All right, good evening, everybody. Thank you for coming back again. I was worried there, especially after Madison gave me my grade from last time, so I'm glad that you came back tonight. Tonight is just, you talk about awe, that's going to be the word for tonight. A couple of things I have to clean up from the last one, which I'll do. The other thing is I'll explain the shirt. Don't get to wear this very often anymore, so it's good to actually have it on. But it comes with a disclaimer that none of this is NASA's opinion. They don't sanction me, all that kind of stuff, right? I told you the last time I spent 20 years in the military, and then as a contractor for a long time. And then NASA invited me to actually join them as a civil servant. So I got to actually be a NASA civil servant for a while, until relatively recently, actually. So it feels good to have the shirt back on to represent the organization, at least this way unofficially. Okay? A couple of things to clean up from last time. First off, the thought experiment I did with the Garden of Eden thing, right? If you weren't here, I'm not going to go through the whole thing again. You can talk to me afterwards. I'd be glad to do it for that. But I want to make sure the messaging came across what I was trying to get across on that, for that. If you remember, God gave the instructions there at the garden. Hey, I'm putting this here so you have visibility into my creation on the other side that I don't want you in, but I want you to see the glory of it, right? And that causes some initial, hey, should we even look? Can we do the, and that goes on in the real world, right? Pay attention to what God says and obey that. And he didn't say you couldn't look in there, right? So, also, the context was missing on everything I explained on the other side. The lights coming and going was actually a day. The length of the day getting longer, so it was in the spring. Some days were cloudier. And then that 7-day repeated cycle where there was actually compression waves, sound, coming through and moving the thing, right? All those things are valid science things. You could measure, they're the truth. No context but what God was doing on the other side, which in that thought experiment was just watching the church here through a hole over there, right? Keep that in your mind as we discuss some of the stuff we're going to go through tonight, all right? Second piece, I'm going to actually write on the board this time. Orders of magnitude. To me, this is normal talk. Apparently, to people who are not mathematicians, this is not normal talk. So, I was talking to Madison afterwards. She said, well, you're just adding zeros on the end. I'm like, yes, technically true, but that's not what I wanted to get across. Remember we said 1, right? Oh, let me start. We'll start down here. I said 1. This is 1. We did the finger experiment. Then we went 10, right? And then we went 100 when we lined everybody up. And then we imagined 1,000 and 10,000 and stuff, right? People, and this is everybody, we tend to jump to the easiest thing all the time. And the easiest thing to do is say we're just adding zeros on the end and call it a big number. What I want you to understand is there's a lot more than just adding a zero on the end. Every time you add a zero on the end, you have to go through this process every 10 times to get to another zero. So the bigger these numbers get, if you add another zero, an order of magnitude, you're doing something big. Yes, ma'am. Did you have a question? Oh, okay. Okay? You're going to want to jump to the easy, we're just adding numbers to things, zeros. Don't let yourself do that. Try to think through what you're actually doing when you see and hear these numbers. Okay? Clear as mud? Okay. All right. So this is week 2, the universe. All right, Jason. I just did the basic review of what we did the last time, which was setting up a lot of the theology of what's in the Bible, where it comes from. Should we even be asking these questions, right? Although there's a counterexample of the Amish, I think the general Christian community has said, yes, it's beneficial to ask these questions and explore what is essentially the mind of God. All right? With the takeaways of doing the stage settings and the other things that we'll come back to. All right? By the way, this is Jupiter with some of its moons taken by the Hubble Space Telescope. Okay, Jason. So this time we're going to go big, really, really big. All right, so ready yourselves. Ready yourselves for what big really is, okay? All right, Jason. First thing I need to talk about, the speed of light. This measures, when we say the speed of light, we're not only measuring a speed, we typically measure a distance as well. A light year is a year, how far a light will go in 1 year. It's also a distance, and it's a time, right? It's approximately 186,000 miles per second, or 671 million miles an hour. That's a lot of zeros. That's a big number, right? Next slide, Jason. This is a well-established scientific fact, as we understand it. We can measure these things, right? And it seems pretty fast to me, 186,000 miles per second. We're going to talk week 4, if you come back, about light specifically. But for this one, we just need to know that it is fast, and it is a measure of time and distance. Okay? It's the ultimate yardstick of time and distance, actually, because nothing that we know of goes faster than this. Okay? Everybody with me? Okay, Jason. So we're going to talk about telescopes tonight, and here's one that Adam brought in, one of the terrestrial versions. But most of the ones we're going to talk about are just scaled up versions of that. And the first one is the Hubble Space Telescope. It is the first major telescope observatory put into space. It's about 340-ish miles up in space. Been there since 77 maybe? 87? Can't remember exactly. It's been there a long time. No instrument we have ever made has done more for science than this one. There are more papers in peer-reviewed journals from this one instrument than any of the others by a long shot. There's not even anything close. It's a unique asset. Okay, Jason. This is it in breaking out, and I ask you to pay attention up front here. Here's where the light comes in. The big mirror is back here, right? That little thing right there is a secondary mirror that catches the light from the primary and then shoots it right in the middle. There's a hole right there onto the focal plane, and the focal plane is just where the light comes into focus on, in this case, an LCD, right? That 4 spokes matter. This is actually the orbital path as it's in space. And if you did an arc on the Earth about it, it would kind of do a nice easy sine wave across here, back and forth across the equator, right? Not very tilted, but tilted a little bit. And it's out there in space. Been there a long time. They've been up to it 3 times with the shuttle. First to fix the optics that were bad when it first got up there, and then to replace a lot of the control mechanisms that are getting old. That's the size of the mirror, right? So it's 7-ish, 7.2 feet. So think about how big that is, and that telescope sees a lot. This is 7 feet mirror, right? Okay, Jason. All right, so let's start taking the tour. And first place we'll go is Andromeda. Andromeda is the nearest galaxy to us, the Milky Way. The nearest big galaxy that is like us. This is called a spiral galaxy. We think the Milky Way is also a spiral galaxy. We can't see that because we're in it, but we think that is a spiral galaxy that does something like this, right? Kind of looks like that, Andromeda. We think the Milky Way is what's called a barred spiral galaxy. So there's kind of a bar of central stars in the center of it. Again, we can't know for sure because we can't see outside it. In this picture, there are two smaller galaxies, one right there, called elliptical galaxies, much smaller than a galaxy like ours, like the Milky Way or like this one. And these galaxies are actually going to eat that up, eat those smaller ones up. They're bound gravitationally, they will get pulled in to Andromeda in this case. This one is in the foreground, I think that one's in the background to Andromeda. The stars you see out here are not out there. They're actually in our galaxy, and we're just looking past them, right? Those are close in. So, let's do an experiment. Oh, guess how many stars are in there? Approximately 600 billion stars. Put your little caps on and you're going, I'm adding zeros, and realize what those zeros mean every time you put another one on the end of it. And I'm going to show you an example of how dense this is in a minute. Okay, so let's do a thought experiment. Let's say I can take us at the speed of thought. Bam, we're halfway between Andromeda and the Milky Way. So we're the first humans that get to turn around and look at our own galaxy, right? One problem is I can't speed of thought us back. I can only do it one time. So I brought along a spaceship, and it's a really good one. It can travel 99.99% of the speed of light. So it doesn't break the rules of physics, but it's a really good spaceship. We're out there halfway between the two, and we go, okay, that was nice. I got the picture, and now I'm going to go home and be famous. Okay? We get in our spaceship, we aim home, and I hit the button. Boom! We hear the engine spool up, whoop, and nothing happens. We don't, you don't get the Star Trek thing, right? That ship is traveling at 186,000 miles per second. It will take us 1.1 million years to get back home. That's halfway. Ruminate on that for a second. What does that mean? We will never be able to interact with that galaxy. Ever. God has put it there, and yet it's a look you can't touch thing. Right? How sad that we can't get there, but the imagination of what could be there is amazing. 1.1 million years traveling at 186,000 miles per second. It would take us 1 million years to get back home from the halfway point. Okay? That's how big that is. That's how far away that is. These are the scale of things we're talking about here. All right, Jason, go to the next one, which should be a movie. Nope, one more, I'm sorry. Okay, play this, and we'll play it twice. Just watch. That was the density of stars in that part of the Andromeda Galaxy. The ones we could see from 2.4 million miles away. And it's not even the dense part. We're focusing in over here. Imagine what it is down in here. Jason, can you play it again? These big ones are stars in our galaxy. Look at that. Each one of those is stars. Who knows if there's planets, what they could be in there. There's that many of them in these big galaxies. And that's the closest one. Was there? Okay. Jason next. So they got the telescope up there and they looked at things like that, right? And then they said, let's just point it somewhere and we're going to look at it. We're going to leave it for 100 hours. Just stare at the same spot for 100 hours. And let's see what we see. This, Jason, go to the next one so it blows it up. I want everyone to take your finger out, take your thumb, put your thumb up, arm's length. Your thumbnail is about the size of that spot of space in the heavens. There's that much there. So let's talk about it a little bit. These things that you see with the crosses are stars close in. They're actual single stars in our galaxy that we're looking past, right? The way you know it's a Hubble Space Telescope is you see the four. You see the four cross like that? And it's a space telescope image. It's almost certainly a Hubble telescope. So when you look at this, there's only 1, 2, 3, 4, 5, 6-ish stars. Everything else is a galaxy, holding anywhere from the smaller ones, smaller elliptical ones, 100 million stars, to the 600 to 800 billion star galaxies like Andromeda. The size of your finger nail. Now keep doing that. That's out there. That's all out there. And you can see it. Elliptical galaxies are these kind of fuzzy ones. You see a lot of the swirls from what we call a standard galaxy. Some interesting things in here that Einstein postulated would happen, but we never saw it until the space telescopes. And that's these little squiggly lines here, which are gravitational lens. I guess I'll have to draw on this too. So right out here we have a big, probably several galaxies in there. And we'll call it like this, right? There's a big galaxy in here. A lot of stars, very dense. There's a galaxy back here, and we are over here. Einstein says mass, he postulated at the time, that mass will bend space and time. What does that look like? The light leaving this source goes by this galaxy, the gravity bends it, and then so we're back over here and it comes into focus again. And it bends around these objects. That is what these lines, right there, some right there, you can look on and see them. Those are galaxies behind the other galaxies that we're seeing because of bending space-time. Right? Don't picture this as a plane. This is depth. Close-in stars, maybe 5,000 light years away. Midway, 800 million light years away. And some of those small ones in the back, especially if they're red, maybe 1 billion, 2 billion light years away. You see? I look at that every time I look at this picture. I hear in my head, stop, don't you're fighting, be still, and know that I'm God. Every time I see it, and I've looked at this a lot, I hear it in my head. Your ways are not my ways. Your thoughts are not my thoughts. So, they just picked a spot to do this. Then they said, we're going to pick an empty spot. Something where it's an empty part of the space as we know it. And we're going to look there. Okay? Did the same thing. 100 hours. They stared into nothing. There was nothing there. Jason, go ahead. This is what they found. There's just as many galaxies as there was in the last picture, they're just smaller because they're further away. Billions of light years away. And you notice they got that redder color, that's the redshift, that's how they know they're that far away. I'm not going to go into Doppler effects, but this is empty space. There's not supposed to be anything. There's one star in our galaxy you can see on this. You see it up in the top right? It must be very dim. Oh, you hear it? There you go. It's my cat's play toy, so it's the best laser pointer I got. We're living on a budget here. But I want you to soak that in, what that means. What does it mean to us? Off limits, we'll never be able to talk to them people. We'll never be able to go there. We'll never be able to communicate with them. The only thing we get is what we see. The only thing I can, and again, this is just me, as an opening statement, I said this is just my interpretation of things, is we have trouble with big numbers. We say routinely, God is infinite. And we blow it off. Maybe he wants to show us a little bit closer to what infinite really is. At least that's what I pull out of it. I'm not a theologian. I'm not a true scientist, astrophysics. That's the only thing I can get out of that. And the wonder of what must be out there. And the desire to so badly go see. And explore. And imagine. They think they found planets that are just solid diamonds. They think they found planets that rain titanium. They found stars that are bigger than our entire solar system. It's all out there. And it's just amazing. Okay, Jason. Any questions on that? Anybody brave? And again, what to make of that, again, the only thing I can come up with is he just wants to show us how big truly is. And it's still a limit. It's still a limit. But as you know, when Abraham was walking around, a mountain was big. The Sea of Galilee was the sea. As we get smarter, we get, oh, well, God's not that big. Duh. Every time we look, he gets bigger and bigger. It's not the other way around. Okay. Now, how he did it, I don't know. I go back to my church wall thing in the garden. He didn't tell us. He doesn't tell us. I don't know. It's there, but this makes me believe all the more that he created it. Just looking at this. Because you cannot convince me that all this just happens, despite how big it is. We, as far as we can tell, when we look back at these things, the atoms, the molecules that we see signature are exactly the same as the ones floating around in you. But we're different. We are the exception. Man, I would like to see what was out there, though. Okay, next, Jason. So that was the Hubble. That's one. There's a bigger one out there now called the James Webb Space Telescope. This one is 21 feet, so it's 3 times, right? So it's really 9 times the surface area for the telescope. It's very unique. Beryllium backplane sits out. I'll show you in a minute. It's gold. The mirrors are gold layered. Beryllium's interesting. Anybody ever had to deal with beryllium? Probably not. So we were building a telescope for NASA, and they wanted to use beryllium. And the reason you use beryllium, it's like 1, 2, 3. It's the 4th element, I think. So it's one of the first metals. It's very light, lighter than aluminum, and stiffer than steel. Not stronger, but stiffer. It also does not contract and expand with heat like almost every other material does. Pretty much every other material does. And it does a little bit. So it's perfect for space things. We were going to put one up for NASA on a CubeSat, so it was much smaller. And we were trying to move beryllium around in the US. It's highly lethal in its powder form. If it's just on the satellite like that, it's not bad. So you have to be very careful transporting it. And it's also very important to the nuclear enterprise. So they watch it carefully. I think I can say all that. And so we had to move it around, and it's a nightmare. The only place we found to store it eventually is we took it to an Air Force base, and they held it for a while till we could get it to the actual manufacturer who was going to use it. So beryllium, I mean, these are exotic things in every way you can think of, right? Go to the next one, Jason. Here it is as it's being assembled at Goddard Space Flight Center. It's laid over on its back, and they're getting ready to transport it out. Okay, go ahead, Jason. So I was at Goddard December, just before the holidays. I knew I was going to do this, so I wanted to go by the place where they built it. And the image here is the back of the mirror, the back plane. That is what beryllium would look like. And they use as little of it as they possibly can because they want to save weight, but they need it to be stiff. This is a Pathfinder gold plate that they used to test out how the mirrors were going to attach and all that kind of stuff. So these are on display there now outside the clean room where they built it. Go ahead, Jason. And here's a picture I took. This was probably back in 2017, maybe. You can see on this side, they have that outside one folded back. They haven't put the other primary ones on, so the two sides are here, and they're getting ready to put in the back plane stuff on it. So it was in the assembly process. You could go by, it's a big clean room, so you could go by and watch them do all this stuff. The little Oompa Loompa people, you know. Yeah. Okay, go ahead, Jess. All right, so this one is unique in another way, is it's way out where it orbits compared to most satellites. Most of our satellites travel around the Earth, inside the moon area there, right? Hubble is in there. This one, so the primary difference, other than being bigger than Hubble, is this telescope is designed to capture infrared light, which is just below what we can see with our eyes. And heat is really what they're looking at. They're looking for heat sources. So one of the good things is the Hubble dust and stuff in space will block out the light. But infrared is a little bit longer wavelength, so it just goes over that, and you can see it, right? So they need this telescope to be very, very cold. No heat at all. Matter of fact, the structure of the telescope itself has to be extremely cold, because if it has any heat in it at all, it will reflect into that mirror and will look like a hot spot, right? So everything about this telescope is to make it as cold and keep it as cold as possible. So what they do is they will put it out in what they call a Lagrange point, which is a stable orbit point where the centrifugal force of the orbit of the Earth exactly matches the gravity from Earth and Sun. So if you get the satellite out there, it'll stay put on its own. Technically, you got to move it a little bit, and it actually orbits the spot. So those are orbital mechanic things that are very complicated. But that's the spot. It'll stay out there, and you have to use very little fuel to keep it there. It's also 1 million miles further from the sun than the Earth is. So that L2 point is about 1 million miles back behind the Earth in the Earth's shadow, right? There are other points where you can put satellites that make a lot of sense. The other one was the L1 point. That is the point where the gravity from the Earth exactly matches the gravity from the sun. So obviously it's much closer to the Earth. But if you put a satellite there, it'll stay. And that's good one for watching the sun and looking for space weather events like we've been having recently. And then L4 and L5, they collect a lot of asteroids. If you were to go out to those points, there is an asteroid field because it's a stable orbit. Jupiter has a ginormous one. It's a much bigger planet. And then the one just off the screen over here is L3, on just opposite side where Earth would be, right? It would orbit over there. It's a useless one for the most part. We can't get there. Okay, Jason? This is what it fully looks like, right? So the sun here would be at the bottom. Earth would be down here. So the communications antennas and stuff and all the machinery is at the bottom here. This piece is called the solar shades. There's 5 layers of it, extremely thin mylar. Matter of fact, you couldn't touch it, it would break. 5 layers of it, so it blocks off any residual heat coming from Earth or from the sun. And this thing gets down to 2 or 3 degrees above absolute zero and stays out there. And then primary mirror, secondary mirror, and then it goes into the hole there to get to the focal plane and all the instruments inside. All right? There was like 112 single points of failure on this thing. Meaning that if one of those things didn't happen, the, $3-4 billion observatory would not work. And it's 1 million miles away, so you can't go fix it. So that's why they took all the time to do the test. That's why it cost $1 billion, right? To get out there and see this stuff. Okay, next one, Jason. It's done the same kinds of things. In this one, you can see the gravitational lensing a lot. I don't want to do this again. A lot better on some of these. Again, because dust and stuff doesn't block those fainter images. So you see a lot of those straight lines or the squiggly lines. Look what it did to that galaxy. That galaxy is probably behind it, that blob, so it kind of distorts it as it goes around the curved space-time. But same picture, right? I love these passages. You just. Okay, Jason. Some more. So this next part is just some images that these telescopes have taken for us to see. Two galaxies, one just in front of the other one, 200 million light years away. These stars, see now we don't have 4. This is the signature of the James Webb. This one's actually so bright you get 6, but you get 8, but you'll see 6 prominently. And you can see other galaxies in the background here. Okay? Jason? Beautiful pictures. This is one of the more famous pictures that both Hubble and James Webb have taken. This is just dust in the middle of nowhere in space, right? These areas where they're clumped up, stars are being born. The gravity starts taking effect. It starts pulling in more and more. We'll talk about stars next week in detail, the most improbable objects in the universe, if you ask me. But this is where they form. This stuff comes together. This is hydrogen, oxygen, helium, a little bit of gravity, and all of a sudden you start collecting it. It starts coming in, and eventually a star is born. This one not too far away, 6,500 light years, so relatively close. Okay, Jason. Another nebula from a Hubble image. There's another one out there, and I should have tried to find it, that focuses in right up in this area here where you really can see a bright light starting to shine in the dust, where new stars are coming from. All right, Jason. Beautiful Helix Nebula. This one is close, 655 million years, or 655 light years away. It's about, I think, 3 light years across this bubble. To give you a size, it would take you 3 years to transit. For comparison, the closest star to us besides our sun is 4.2 light years away. Right? So it's fairly, depending on your standard, small or large. But there's a star at the center, white dwarf. It ran out of its primary fuel. Once that happened, it collapses and explodes and blows off all this stuff that used to be the star. Okay, Jason. Now, they recently did, all right, this one I want you to flip back to again, Jason, backwards. So this is an area down in here where they zoomed in and looked really closely. All right, go ahead, Jason. And you can see it's blowing the dust out from where that star was. Also, some really cool things here. These are stars between us and them, probably. In the background there, look, you can see a galaxy, galaxy, galaxy down in here, galaxies up in here. They're everywhere. You don't have enough imagination to imagine all of them, right? Okay, Jason. Another beautiful one, 7,500 light years away. I'm just giving you these so you, again, put your imagination to work at what this is and what it means. And they're out there, all over out there. Okay, Jason? Another beautiful one. Okay, Jason? There's clusters of stars in our galaxy that are very dense. They're called globular clusters. There's a bunch of them in our galaxy. This one happens to be about 17,000 light years away. And it just kind of shows you how dense these things can be packed in together. And the different kinds, different colors. And again, you don't imagine this as a plane. This is a ball, or at least a deep field, right? If you moved it, it would move around. Okay, Jason. Oh, this is a beautiful galaxy. Edge on, right? So you're looking into the plane of the galaxy and you're seeing all, the line is all the dust and stuff that's being circulated around the spiral galaxy. Again, this looks like a cloud of white stuff. Those are stars. Right? A lot of stars. Okay, Jason. Another ring kind of nebula, same sort of thing as the last one. This one's a little bit smaller, only about a light year. Okay? Bubble nebula. This one was found a long time ago, 240 years ago. So, you know, somebody was looking at it. All right, Jason. We're not done. We're making more telescopes. So, this one, I took this took the picture on the right. Again, it was mid-December or so. This is the Nancy Grace Roman Space Telescope. The same. It's actually the exact same mirror in Hubble. So when they made Hubble, the secret spooky people made 2 or 3 other mirrors. I know of 2 that they made. I don't know how many they actually made. But eventually they ended up not needing one, so they let it come out into the open and said, we're going to gift it to NASA if you guys want it, if you can make a telescope out of it. So they did, and they made this telescope. Here is kind of just the mirror itself and some of the instrumentation that goes on it. Here it is, the mirror with the sleeve, just like this sleeve on this thing here, is on it, and the solar panels on the back end. This one will also go out to where James Webb is, way far away, right? Okay, Jason. So this one is built different, okay? And I took this picture to hopefully explain to you the difference. So Hubble is looking at the thumbnail size at a time. This one will look at kind of the palm of your hand. So they'll focus it different. And the difference is, see these little blue things? These are focal plane instruments. Hubble just had one. And you see that really faint box here in the middle? That's what Hubble will see versus what the Roman will see. Right? So it won't be able to focus in as tight, but it's looking broadly at the stars in the universe. And they'll use it to search for planets and to, okay. So there's this, the Big Bang Theory isn't correct, and they're starting to see evidence of it. And one of the things is, close-in galaxies, the expansion rate of the universe is like 6.24 parsecs per kilometer per second, some crazy number. If you look back way in history, it comes out to 7.4 or something. So there's a disconnect. There's something wrong. It shouldn't be expanding quicker. Older we are, it should be a constant rate. One of the things that they want to do here is take more accurate measurements of close in and far out to see what is the problem here. Because as it is now, that should not happen. So that's what one of the things this telescope is going to be doing. Probably didn't explain it right. I'm going to get some dinged on that when I go home and get my grade, but bear with me. Yeah.
Is there an article or something that you could direct us to that argument about Big Bang Theory not being correct based on the expansion of the universe?
Actually, there is one. It just came out relatively recently on space.com, I think. I'll see, and if I can, I'll send it out. Yeah, because it explains better than I can that difference. Okay? I showed, if you were here last week, the comet that we landed on. This is a picture of us, of the lander getting close to it, right? This thing is orbiting around. Okay, Jason. This is very close, just before landing. It's a comet. It's a ball of ice and mud, not mud, frozen. Ice, water, rocks. For however long it's been circling the sun. Okay? Perspective. Perspective is everything. We have a satellite orbiting Saturn, and they turned the camera and took a picture of us. That blue dot is us. A speck in the middle of nowhere, going nowhere. Perfect for us to live on in every way. That's Saturn. That's the rings. There's the edge of the planet itself. Truly, truly amazing. Humbling. I think God wants us to stay humble. That's the only thing I can come up with. That's the little blue dot. Tiny. Middle of nowhere. In a galaxy in the middle of nowhere. Others out there we could never get to. All right, I think that's it, right, Jason? I don't know that I can do any better in trying to get across to you the amazement of just picking into what God has created. To me, anyway. I'm hoping you get some of that and got it across. If did, then that's all I wanted to do. I always read the Bible, the where Jesus said, if you had enough faith, you could make the mountains fall into the sea. I'm like, Then I see this. Well, that's trivial. It's not even in the consideration of trivial. When God can create stuff like this and put us in it and show us how we are compared to Him. Right? That's it for tonight. Right on time. Yes.
One of your slides alluded to determining the age of the universe, but
Yeah.
didn't really dive into it. Based on the number of light years that some of these images are coming from, can you just briefly chat about that?
Well, so again, we can see back. The earliest galaxy they think they've seen is 12 billion years, 12 or 13. They say it's 13-ish billion years old. I'm looking through such a tiny hole. Yeah, I'll buy that. How that matches up with 6 days of creation, I don't know. God didn't tell me. I'm going to take Him at His word. If He can make this, I have no question He can make it in 6 days. That's trivial, right? Where they don't mesh, we'll find out one day, hopefully, right? But He just hasn't told us, right? Maybe Adam knew. I don't know. But this is a time. This is not just distance. This is time. That galaxy, the Andromeda galaxy, could have gone. It's done. I'm taking it back. 2 million years ago, and we still would never know it. Right? Still 100,000 years before we would know it. So you have to take this with granted. Something that's 2 billion years out. God could have had, who knows what He's doing? He didn't tell us. He's letting us look through a really tiny straw at His creation. And we just can't see. I don't presume, I don't have that much hubris to really be able to say that, right? So I take it at face value. Yeah, science says it's 13 billion. It was created in 6 days. I don't know how to reconcile them. But I'm not going to be scared to say that either, right?
Amen, John.
Yes, sir.
Isn't it also true that there's light still coming to us that may not have gotten here yet? So it's even bigger.
Oh, yeah, yeah. So there's actually a theoretical size that we could see, and it's big. I don't remember the exact number. And since the university is expanding, there's a point where it's expanding fast enough light will never get back to us, right? And that's kind of an event horizon of a black hole. But it's possible. We don't know. We don't know. Yes, ma'am. Who is man that you should consider us, right? That's all. I said, you just read those verses, just fall out when you see stuff like this, right? My goodness, yes, Adam.
I've seen a lot of scientists take the scale of the universe and they take the exact opposite conclusion. And they'll try to belittle man. They'll say, look how insignificant we are. We're nothing more than a tiny speck of dust. Where do you think the fallacy lies in that argument?
So the perfection of that tiny speck of dust, right? And we may get into this on the fourth weekday presentation. There are so many things that have to be perfect for us to live here. And the most brilliant minds who have thought through the history, if you go and read their biography, at some point they go in there, God, some power had to do this to make it this perfect. And especially for this planet. I mean, those are just the math and the weak force and the strong nuclear force and all that, those things. But added that, we're at the bottom of a fluid that is just perfectly dense, perfectly temperatured, perfectly protected from a nuclear bomb for us to live quiet, peaceful lives. Come on. I can't eat. It's easier to believe. It's actually easier to believe that God just made it. To me. Again, this is just me. You talk to the preacher and stuff afterwards if you disagree with that. Yeah. Yeah. Teeny. A moat. Might. Right? Okay. Next week, we'll talk about the sun in detail. Right? And I feel a little more comfortable speaking about that one since I just came out of this heliophysics guys at NASA. So hopefully we'll get some good stuff there. We'll talk about the sun as time allows. We may get into some of the planets in the solar system. We'll see. Yeah. So this is the sun back in 2025, February 27th. Beautiful. This is hydrogen L1 line, and I'll explain some of that, what that means. You can see the magnetic field lines, you can see the solar wind, those kinds of things. And again, we're going to talk about numbers that you're going to have to think again outside your normal thing when we talk about the sun. It's an amazing piece of creation. Okay? Thank you so much for coming out. You have 2 minutes left, sir, for your sermon.
Let's give him a hand.